Picture a group of friends standing in a circular formation, passing a soccer ball back and forth to each other. Every player has their turn to kick the ball randomly to another player in the circle, allowing the ball to move around unpredictably from one player to the next. When playing a game, one person may like to show off their skills. Instead of simply passing the ball to another player, they might do some fancy tricks like juggling the ball with their feet and knees before finally passing it on. This makes the ball move in unexpected ways, but it still stays within the boundaries of the circle. The idea of resonance is surprisingly similar. All matter is composed of atoms, and inside these are even smaller subatomic particles known as electrons. When a large group of atoms bond together, we call it a molecule. Basically, a molecule has many atoms, which themselves have many electrons. However, these electrons are not stationary. They keep moving around, and they do so in unexpected patterns. Resonance happens when these electrons jump between different positions within a molecule without compromising the structure and stability of that molecule. To understand resonance in more detail, you need to know about three things: covalent bonds, sigma and pi bonds, and Lewis structures. Since a molecule contains many atoms, and these atoms contain electrons, as you can imagine, these electrons interact with each other. Atoms sometimes share electrons amongst themselves and become more stable. This type of sharing of electrons between atoms to achieve greater stability is called covalent bonding. There are three main types of bonds, dependent on the number of electrons shared between atoms. If two atoms within a molecule share a single pair of electrons, a single bond is formed between the atoms. Similarly, double and triple bonds are formed when two atoms share 2 or 3 pairs of electrons, respectively. Covalent bonds also come in two types: sigma bonds and pi bonds. Sigma and pi bonds are made when atomic orbitals overlap. But what are atomic orbitals, you may ask? As mentioned earlier, electrons don't stay in one place, but are instead constantly moving. The spaces where the probability of finding electrons is the highest are called atomic orbitals. A sigma bond is formed when two molecules bond and their atomic orbitals overlap head to head. On the other hand, when the atomic orbitals overlap side to side or laterally, then a pi bond is formed. We can understand sigma and pi bonds using a dance analogy. Imagine a sigma bond as a direct face-to-face connection, such as when two dancers hold hands in front of each other while dancing. In this bond, two atoms share electrons by overlapping their electron clouds head-on. It's like both dancers are facing each other, sharing a close and strong connection. On the other hand, a pi bond is like a sideways connection. Sometimes, in line dancing, for example, you might hold your partner's hand to one side, forming a less direct connection. That's why a pi bond forms a weaker connection than a sigma bond. And finally, what's a Lewis structure? A Lewis structure is a tool to represent valence shell electrons in a molecule. A Lewis structure shows the arrangement of electrons around individual atoms in the molecule. Electrons are shown as dots, while bonding electrons are denoted as a line between the two atoms. Now, how does all of this explain the idea of resonance? Well, electrons in sigma bonds tend to be in specific locations, which is why those electrons are said to be localized, whereas pi bonds have delocalized electrons. These are found above and below the atoms and are spread across several atoms. You can think of resonance as a way of describing delocalized electrons within certain molecules where a single Lewis formula cannot express the bonding. Benzene is a chemical compound that has a hexagonal ring of carbon atoms. The ring contains alternating single and double bonds. Trying to represent benzene with a single Lewis structure wouldn't accurately depict its chemical properties. Therefore, we need resonance structures to show benzene's electron distribution accurately. Think of benzene as a group of individuals standing in a circle, holding hands and dancing together. In a typical scenario, they would be paired up in a waltz, some holding one hand of their partners while others hold both. In reality, however, everyone is dancing as a team in a circle, with their hands constantly moving. Just as in the case of benzene, the idea of resonance helps us understand and describe molecules that a single Lewis structure cannot represent. The various resonance structures show different possibilities of the electron's positions in the molecule. It's a bit like watching that soccer ball being passed around in a circle of players. Although the ball moves in an unpredictable trajectory, it always remains inside the circle, ensuring that the game runs smoothly.